All right, so now let's talk about orbital shapes. And this is going to lead back into the Schrodinger wave equation. Like I said, we're not going to solve it here, but the result of it is these electron probability or density clouds. And so these basically tell us where an electron is going to be, or the probability it's going to be somewhere. And so oftentimes you'll see these shapes represented as solid shapes, like here. So this is meant to represent the electron density and to show you where it is. It's in these shapes. There's this plane here. This is called a nodal plane. That means that there is nothing there. So it's an empty spot. And so basically either here are where we're going to find the electrons. However, this could be a little misleading because this is a solid shape, but the probability is not uniform throughout this shape. What we should kind of show is something like this. And so this is just a cross section, but you can see here kind of from the dot intensity is where the electrons spend the most time and where they spend the least time in that shape. So you can kind of see that they're concentrated here and here, and then it gets less dense as we go out from that center point, right? So that's more of what it looks like, and that's what we're going to see with all of these. So whenever you see these shapes, keep that in mind, that it's going to look more like it's going to look something like this, where it's not a uniform density throughout this shape. So keep that in mind when we're looking at these shapes. All right, so let's take a look at some of the various shapes we can see for orbitals. And so these are the p orbitals. And so remember, this is the L equals the second quantum number. So S is 0, P is 1. And so with L equal 1, we have three. We have values of -1, 0, and 1. And so we have three different orbitals. So these are kind of for the n equal 2, these are labeled as 2px, 2py, 2pz. So these are the three different orbitals. And what these shapes kind of show us is the spatial breakdown of where an electron spends its time. So for this orbital, there's concentration on the x-axis, so that's why it's labeled with the subscript x, because the electrons spend their most time around the x-axis. Same thing for y along the y-axis, and z along the z-axis. But basically we have these two orbs with a nodal plane in the middle for each. So in any of them, we're not going to see stuff at the origin of this system. So that's what we kind of expect for 2p electron orbitals. If we look at the d orbitals, in this case the 3d, and you go through the same kind of math there, we're going to expect 5 orbitals because we have -2, -1, 0, 1, and 2. And then, so that gives us the 5 orbitals. And by solving the Schrodinger wave equation for this structure, we see where the electrons spend their time, and the shapes get kind of more interesting here. But we still kind of have these lobes. And in this case, all of these have two nodal planes or surfaces. And so that's what we see in these cases. But again, a little bit more complex, but the naming system refers to where the electrons are, or where the nodal planes. So in this case, XY kind of indicates the nodal planes here. And so these 4 look very similar, but you see the z squared down here is quite a bit different, where you have this more donut shaped with lobes on top and bottom of it. So there's a little difference in the shape of these. But the important thing here with all of these is that this allows us to understand spatially, like within the atom, where electrons are located, because this is going to be important for a lot of properties down the road, the spatial location of various electrons. All right, and I want to make a note here about symmetry and the sign of the Schrodinger wave equation. So this shows some various orbitals, and here we're just showing the two-dimensional representation of it. So this is an s orbital where we have a sphere, and the sign of the Schrodinger wave equation is positive throughout. I want to make it clear here that this is not the sign in terms of charge, right? Because electrons are always negatively charged. So if we're talking about the electron cloud, it's always going to be negative. But here we're talking about the sign of the Schrodinger wave equation. So in this sphere, the sign is equal throughout. Whereas here, it's positive on this lobe and negative on this lobe. And you can see that positive, negative listed throughout. If we go back here on these more three-dimensional models, instead of a sign, we see them represent the sign of the wave equation by color. So yellow and blue mean alternating sign in the Schrodinger wave equation. So that's what the color means in terms of these representations. Same thing with the 2p. All right, so when we talk about symmetry, then we're talking about the same sign. So if we invert something through the center, so we're talking about the center of the axis here. So this is the center. So if we look at something at point A, and then we invert through the center, so we go through this and to the other side. So it's like taking the point values of A and making them negative, and that gets us to point B. We look at whether it has the same sign. So here, A is in a positive portion and B is in a positive portion, inverted through the center. And so this means it is what we call gerade, which I believe is a German word, but it's not necessarily important for this. But this is gerade if it has the same symbol throughout. So this one is gerade. If we go to the next one, A here is in the negative sign, and we invert through the center, go to B, it's in positive. So this is, if you might imagine what the opposite of it is, it's ungerade. And so you can do that for all of them. And this just tells us about the symmetry with the relationship to the wave equation. And so if we keep going here, positive, and then positive on the inverse side, gerade, positive, positive, gerade. And then if we take any of these spots, positive goes to negative, negative goes to positive. Anywhere you invert, it's the opposite, so that is ungerade. And so that's how you kind of look at symmetry in these orbital shapes.